All right, and we're going to finish this chapter with just one example, an application of the theory where we're going to compute a probability of extinction. And as you can see, we're going to do it for a certain binomial with parameters 3 and p. Let's get to it. So hold on, there we go. Yep, all good. So example number 21. Let's be conscientious about our numbering. Sometimes. Example 21. So it's the probability of extinction, for binomial, bin means binomial, 3p. Okay, so we're just gonna compute it. Now, I'm not gonna call it q like before because we're gonna use q as 1 minus p as we've done earlier, but that's okay. Let's write down the whole question. So consider a branching process with offspring distribution, which is binomial. So with binomial offspring distribution, with parameters 3 and p, where p is just a number between 0 and 1, of course. So we're going to ask two questions. So first, so for which p is the probability of extinction equal to 1? Writing this fully. That's a question mark. And when it's not 1, can we actually compute it? When it is not 1, find it. Now, you know, this is a long-winded way of just asking what's the probability of extinction, but I like distinguishing when it's 1 to when it's not 1, because as we've mentioned, when it's 1, it means we're critical or subcritical. So there's something different in terms of how you actually compute things. And we will see that it makes sense to really separate the cases. So that was the question. Let's do the answer, maybe a bit of setup. Okay, so setup that we know is, we're going to use q equals 1 minus p. That's useful. And we're going to write x be the probability of extinction. Probability of extinction. And x is fine. S, if you want, any letter, of course, will do fine. So we know the offspring distribution. It's binomial with parameter p. So we know that p0 is q cubed, p1 is 3q squared p, p2 is 3p squared q, and p3 is p cubed. That's the binomial probability distribution. So the probability of getting 3 successes is p times p times p. And 1 and 2 have the 3 in the middle because that's the 3 choose 2 or 3 choose 1. Now, one thing that we know, of course, is that the mean of this distribution of binomial 3p, the mean, the expectation, is 3 times p. Okay, in general, it's n times p when it's binomial np. Here, n equals 3. So this means, by the theorem, that x equals 1 is equivalent to p less than a third. So if you have a possibility of 3 children, but each possibility only has a probability less than 1/3 of happening, then on average you have less than 1 and the process dies out. So that technically answers the first half. Let's box it, especially since I have the tools to draw some nice boxes here. I recommend boxing your results. It helps whoever reads them on an exam script. So we have that, and when p is bigger than 1/3, we'll be able to actually compute it. So for p bigger than 1/3, we have that x is a solution to an equation, which is given by all these probabilities that we have above. So I'll scroll up a tiny bit. X equals q cubed plus 3q squared p x plus 3p squared q x squared plus p cubed x cubed. Now, okay, this is a polynomial. We know more or less how to solve these equations, right? We know how to do them in degree 2 because it's a quadratic formula. Here, this is degree 3, so maybe it's a bit harder, but we'll see that we're going to be fine. The first thing to do when there's a polynomial is really just write it as polynomial of x equals 0. So quick rewrite. So we're going to write q cubed plus 3q squared p minus 1 x plus 3p squared q x squared plus p cubed x cubed. That's a cube over there. It's a squared. That's a cube. Equals 0. And so, usually this is hard to solve, but remember, it's quite important because it's very useful here. In general, we know that 1 is always a solution of this thing because 1 satisfies f of x equals x. So given that this is a cubic equation, I know that I can factor out x minus 1, then I'll be left with a quadratic equation. So we know, or you can check it if you like, that 1 is a solution. So we can factor, magic of polynomials, we can factor in x minus 1, which means we're going to get, we don't know quite yet how it looks, but I can write it something like x minus 1 times ax squared plus bx plus c equals 0. And I need to find my capital A, capital B, capital C. And I can do that. It's not too bad. So how do I do it? By comparing, coefficients corresponding to various degrees. So for example, p cubed x cubed needs to come from ax squared times x, because that's the only way I'm going to get a cubic degree out of this. So a equals p cubed directly. That's fine. So from the green. Similarly, c times minus 1, that's going to be the only constant degree thing here, 0 degree, which means it needs to be q cubed. So from the red, we get that c equals q cubed. Now there's a minus sign because there's a minus here, of course, and there's no minus here. And so we found A and B easily. Now A and C easily. B is a bit harder because if you think about it, well, we're going to have things mixing up. The best thing you can do is this 3p squared q, which is the factor of x squared, I'll put it here, is going to come from a times minus 1 plus b times 1. So, the invisible 1 in front of this x. So here maybe I'll write it in English because otherwise we'll get a bit confused. So black. So identifying coefficient of x squared. This is what you should be writing everywhere. Identifying the coefficient of, or just say one big sentence identifying all the coefficients, we get 3p squared q equals minus a, sorry, I'll erase that dot, minus a plus b. Yep. And of course, by that, I can figure out what b is. So b is, there was this p cubed here, so 3p squared q plus p cubed. Absolutely. Just checking my notes. So we have these three, which means since we know x is different from 1, we said it, we're literally in the domain where this doesn't happen, we have a quadratic. So that's going to be a bit easier. So p cubed x plus, p cubed x squared plus 3p squared q plus p cubed x minus, q cubed, nothing, equals 0. So that's a quadratic. We can solve it, it's fine. And as you know, the best way to solve quadratics, well, maybe you don't know. The way I prefer doing it is simplifying. So we're going to get just x squared in front, and then we're going to get 3. So we divide everything by p cubed, basically. So if you think about it, we get 3q over p plus 1 x minus q over p cubed equals 0. You see all of a sudden it's like q over p is the important thing, not just p or q, it's really just q over p. And having this, I can write down the solution pretty directly. It's minus b plus minus square root of delta divided by 2a. Yeah, there you go. So we're going to get x is half, that's divided by 2, of, so minus b, minus 1 minus 3q over p, plus minus square root of 1 plus 3q over p squared plus 4q over p cubed. And there's a plus minus, that's no good, because we want one value. We know there's only one value. But if you think about it for a second, if you take the minus will give you a negative value. So it cannot be the minus. So the minus in plus or minus gives a negative value. But x is non-negative, so there's only one value left. So we must have x equals, I'm going to write the same thing, but just put a plus in. X is half of minus 1 minus 3q over p plus square root of 1 plus 3q over p squared plus 4q over p cubed. Now, formula is a bit messy, absolutely, but that's not the point. The point is we've been able to compute the thing, and in particular, plug in q is 1/6, and you will get a value, an actual probability of extinction for your branching process. And for that, we're quite happy, quite grateful that this is actually doable. I should mention one thing, which I didn't quite mention, but we always, unless I say we don't, we always start from z0 equals 1. So the population starts with an initial person. And if you start with z0 equals 3, then you would get x cubed as the probability of extinction, similar to the argument we used in the proof. If we start with 3 people, it's like saying we have 3 different processes which are independent, and they must all go extinct for actual extinction to happen. So yes, there you go. There we go. This is the end of chapter 3. We've learned quite a lot about both random walks and particularly branching processes. But now with chapter 4 coming up, we're going to go back to more general Markov chain stuff.